Okay. I'll just, so if there's strange pauses or clumsy things as we go through them, it's because Big Blue Button's behaving in a different way than I expect. One of the buttons I used to have was a go back button that I don't have anymore. You can see that the public chat looks kind of the same, but it's a little bit different. I don't know what we'll see when we do our first poll. We'll just kind of have to roll with it a little. And if today's a little clumsy, figure out that as we continue using this new version of Big Blue Button, that it'll smooth out. All right, here goes. Probability basics. Since we're doing an introduction to probability, we're going to make sure we have some terminology down. And one of those really important terms for us is going to be sample space. And what a sample space is it's all the possible outcomes for a certain event. So something's going to happen. What are all the possible outcomes? A very basic idea is if we were going to roll a single six-sided die. So if we're going to roll a single six-sided die, then the different possibilities, the possible outcomes we could get would be the numbers 1 through 6. And that would be it. 1 through 6 would be all the possible outcomes. So there'd be 6 of them. 1, 2, 3, 4, 5, 6 would be our sample space. Obviously, we're going to see situations where the sample space is more involved than that, but the idea doesn't change. It's everything that could possibly happen. 2 different types of probability. The first we'll look at is theoretical probability. This is what should happen. For example, if we were to flip a coin a whole bunch of times, we would expect about half of those to come up heads and half of those to come up tails. We don't actually have to flip the coin. This is what should happen. It's what we would expect. And this type of probability is calculated. It's not something that we actually flip the coin. We just calculate it based on what we know should happen. This is the type of probability we are primarily going to be focused on, is theoretical. But we are going to see some of the other kind of probability, and I want to make sure you're aware of it, and that is experimental probability. Experimental probability is the result of actually doing an experiment or an activity. What I mean by that is, let's say I wanted you to flip a tack up in the air, and I wanted to know the probability that's going to land pointing straight up. Well, I have no idea what the probability of that is. So instead of trying to calculate it, we would actually do the experiment. We would flip the tack over and over and over and record how many times it landed pointing straight up and how many times it didn't. And we would use that experimental data to get our experimental probability. One thing I do want to say about experimental probability is it has a couple of other names, means the exact same thing. So experimental probability is also known as relative frequency or empirical probability. We'll generally use experimental probability, but these 2 words, if you see them somewhere else, mean the exact same thing. The most important thing about probability, and you'll see there's a whole page dedicated to this because this is the most important thing about probability. Probability is equal to successes over outcomes. It doesn't matter what kind of probability question we're working on. It all boils down to this in the end, that the probability of an event is equal to the number of successes divided by the number of outcomes. So I'll say this over and over and over again, at least today and maybe further. Probability of successes over outcomes. One thing I do want to denote, though, is successes up here. That doesn't mean something good happened or that I win something. It's not really about success in that way. What it is did the thing we were looking for happen? If the thing we were looking for happened, then we call that a success. So just keep that in mind. It's not about winning or something good. It's just, did the thing we were investigating happen? And if it did, we call that a success. All right, let's look at some examples. So a single six-sided die is rolled. So we know that the sample space for this, the list of possible outcomes is 1, 2, 3, 4, 5, 6. There are times when it's useful for us to actually write down the sample space, especially when it's small like this. So there we go. There's our sample space. And the first thing I'm asked here is P3. Well, that notation means what is the probability of getting a 3? So that's what that notation means right there is what is the probability that when I roll that dice, my result is a 3? Okay, well, keeping in mind the main thing about probability is that probability is successes over outcomes. Let's see here. I'm going to ask, you can just tell me, how many outcomes do I have when I roll a single six-sided die? How many different things are there that could possibly happen? That's my number of outcomes. Now I kind of want to see how the chat works. Okay, good. It works. Jennifer, Nadine, and Brianna, you're all exactly right. 6. So we have 6 outcomes. So we know the probability is going to have 6 in the denominator. Now we have to go find our successes. And the number of successes is that's how many ways that this thing could actually occur. Out of my 6 possible outcomes, how many of them are 3? Perfect, just 1. So we have 1 success out of 6 outcomes. So the probability of rolling a 3 is 1/6. If that seems pretty simple, good. It kind of is, right? Successes over outcomes, that's probability. I'm going to ask you to do one. I'm going to set up a poll. We'll see how this goes for the one there at the bottom. Give me just a minute to make sure I work my way through this. Okay, things look pretty good. All right, so I'm going to ask you for the probability of rolling an odd number. So on my side, the polling is a little bit different, but but that's okay. I'll get used to it. So we want the probability of rolling an odd number in this case. So we need successes over outcomes. That's how we get probability. We'll go another 15 seconds and then talk about it. Okay, let's see how we did. A little much harder to read this way, but what I'm getting here is we were unanimous on the 3 out of 6. Well, I don't like that at all. Okay, so what we're after here is successes over outcomes. And I'm sorry, I can't help myself but comment on the changes to Big Blue Button. It's one of those things where it's really unfortunate when these things happen mid-semester and they throw you a little bit. We'll do the best we can. All right, so we want the probability of getting an odd number. Well, that's successes over outcomes. And just like before, we still have 6 outcomes. And now odd numbers. That would be the 1, the 3, and the 5 would be odd numbers. So we have 3 successes out of 6 outcomes. So the probability of getting an odd number is 3 out of 6. This raises a really important question for us. You may be wondering, do we have to reduce that or not? And it's an excellent question because 3, 6, well, you could reduce that to 1/2. And the truth of it is both of those, either of those would be considered correct here. And I'm going to go ahead and let you know that this is kind of a rare case where you don't have to reduce fractions if you don't want to. when they involve probabilities. So for probabilities, you don't have to reduce the fractions if you don't want to. You can reduce it to 1/2. The reason that we don't necessarily need to reduce fractions for probabilities is because 1/2 is absolutely correct here. It's a correct answer, perfectly fine, nothing wrong with it. But in some ways, this answer over here gives me a little more information. Here I can see exactly how many outcomes there were. I can see exactly how many successes there were. And that's why for probability questions, you don't have to reduce fractions if you don't want to. You can if you want to. It's okay. Just make sure you do it correctly, but you don't have to if you don't want to. Try a couple more here. And I'm just going to ask you these. I'm not going to do a poll for it. A single six-sided die is rolled. Find the probability of getting a number less than 15. So anybody who wants to can just type in there, what's the probability if I roll a single six-sided die that I get a number that's less than 15 when I roll that die? And don't overthink it. Okay, I like your sixes, but remember, we're after probability here, and probability is always going to be successes over outcomes. So, very good, Nadine. And so, identifying the number of successes is a very important part of this, but I will kind of nag you a little about making sure that you don't just write the number of successes. And where this page is going actually relates to that. So, okay, here we have 6 outcomes, and well, all 6 of them, 1, 2, 3, 4, 5, 6, those are all less than 15. So we have 6 successes out of 6 outcomes. So 6 out of 6 would be our probability. If we were going to reduce that, write that in a more simplified way, we might say the probability is just 1. That's fine. We could do that here, but 6 out of 6 is great. Okay, similar, but a little bit different. What's the probability of getting 15? So if I roll a single six-sided die, what's the probability of me getting a 15 when I roll it? Excellent. Shelby, Jennifer, you're exactly right. I have 6 outcomes. Well, none of them are 15, so I have 0 out of 6 is the probability I'm going to get a 15. 0 out of 6, a great answer here. If I wanted to simplify that and write it in a different way, I could just say it's 0. If you're looking at these two questions thinking, these are awfully obvious, I don't see the point. Here's the point. What we have here is the probability of getting a number less than 15. Well, getting a number 15 is going to happen every single time. It is always going to happen. And then the probability of getting a 15 when I roll that dice is, well, that can't happen. That's never going to happen. And so what we can see here is something that's never going to happen has a probability of 0. Something that's always going to happen every single time, no matter what, has a probability of 1. What this means is all probabilities are between 0 and 1. So it's a big idea. All probabilities are between 0 and 1. If you're thinking, well, there can't be very many answers for probability questions then. Well, I don't know. Hang on a second. You know, we saw 3, 6 a few minutes ago, but we could have 271 out of 430. Oh, okay. So there's an infinite number of possibilities. We just know that every single one of them has to be between 0 and 1. One of the nice things about this is it's a built-in self-check. You do a problem that asks you for the probability of something, and if you just, you know, weren't really thinking about it and you put your answer was 6, like, wait a minute, that can't be right. All probabilities are between 0 and 1. I need to go back and make sure I'm answering this in a way that makes sense for the question. So it's a really nice built-in thing, and it's a cool property of probabilities that they're always between 0 and 1. Anybody have questions up to this point? Most important thing about probability is right there. Okay, very good. Dice and a deck of cards make for excellent probability questions. So far, we've just looked at rolling one single individual die, but we might roll a pair of dice. And when we roll a pair of dice, if you're familiar with, games like Monopoly or other kids games, you might think, well, the only outcomes are 2 through 12. And you're not wrong if we find the sum of the faces of the dice. But instead of that, if instead of finding the sum of the faces of the dice, we, sorry, um, instead of finding the sum, we just want to know what are all the possible outcomes when I roll a pair of dice. And let's take a look at that for a minute. Now, going back to last week, the fundamental principle of counting would tell me that there are 6 possible outcomes on the first dice, 6 possible outcomes on the second dice, and we'd multiply those together. So altogether, we better have 36 total outcomes when we roll a pair of dice. And that's what you see. Oh, I better not do it because I can't make it go away. That's what you can see over here in this diagram. Not having a back button is going to throw me for a little while. That's what we see over here. We have, 6 rows and 6 columns, and there's everything that can happen. Sometimes when students look at this, they'll see, well, wait a minute, how come you have a 1 with a 2 and a 2 with a 1? Seems like you have that outcome more than once. But I want you to focus in on the actual dice that are there, not the position of them, but the one that's on the left of the 2. It has a 1 on the red dice and then a 2 on the green dice. And the one that's on the right of those, that one has a 2 on the red dice and a 1 on the green dice. And so we can look at those and we can see, hey, between these two, what's actually on the dice has changed. That's what makes those different from each other. It's not that the 2 moved from the left side to the right side. That's not what I mean. So, we have that one there at the top. If we were to put the 2 over here and put the red 1 over here, these two are still the same as each other because the dice didn't change. So those two, there's no difference between those. But these two, there is a difference, and it's because what is on the dice is different. And so that's why a red 1 with a green 2 is different from a red 2 with the green 1. Sometimes that can be sticky for students, so you let me know if you have trouble with it. And then where this tends to go next is like 3, 3 here. Well, how come you only have 3, 3 one time? There's no other 3, 3 anywhere in this picture. And the reason for that is if we have a 3 on the red with a 3 on the green, and then we switch it around so that there's a 3 on the green with a 3 on the red, well, the dice didn't change from here to here. It's still a 3 on the red and a 3 on the green. So these are the same as each other. So we're not going to count that twice. We're not going to have it in the chart 2 times. Please let me know if you have any questions about any of that, because it is something that is sometimes difficult for students to just sort of to manage that one. The idea that, 1, 2, and 2, 1 are different, but 3, 3 and 3, 3 are the same. And yes, that's exactly true. Okay, very good. Let's look at some pair of dice type of questions. 2 dice are rolled. What's the probability that the sum of the faces is 10? I'm going to make a poll for this, and I'm going to put the last page back up there. So we want the probability that the sum of the faces is 10. I'll set up a poll for it. As you work on this one, keep the main thing about probability in mind. And it's definitely the type of question you could expect to see in a homework, on a quiz, on an exam, is find the probability that the sum of a pair of dice is 10. We've got another 15 seconds, and then we'll talk through this together. All right, let's see how we did on this one. Okay, not unanimous, but we do have a majority. That's a good thing. Really don't like that new reporting. I like the one with the percentages way better. Okay, so let's take a look at this. What we're after here is we want to find the probability that the sum of the outcomes is 10. So what we're going to need to do is we're going to find successes over outcomes. We're going to need successes, successes over outcomes. And to get successes over outcomes, we're going to go through this chart and we're going to say, well, I know because there are 6 outcomes on the first dice and 6 outcomes on the second dice that there are going to be 36 total outcomes. So that much I know for sure. And then I have to find my successes. And that's anything where the sum is equal to 10. So as I look through here, well, there's 5 and 5 makes 10. And here's a 6 and 4, that 4 and 6, excuse me, that makes 10. And a 6 and 4 that makes 10. Let's see, are there any other 10s? Well, that's 9, 9, 9, 11, 11. Nope, that's it. One of the nice things about the way this chart is set up is we can kind of see the sums in a diagonal line. All the 10s are here, all the 9s are here, all the 8s are here, and so on. Anyway, when we look at this, we see there's 1, 2, 3 that have a sum of 10. So in this particular case, we have 3 successes, 36 outcomes, and so our probability is 3 out of 36. You could reduce that to 1 out of 12 if you want to, but you don't have to. Certainly on your, certainly in your, on your, when you're working on homework problems and on the quizzes, I haven't thought about that for the exam. Let me think about that, Shelby. I'll get back to you that. Let me make a note. Okay. So what we end up with on this one is 3 out of 36, which could be reduced to 1/12, but you don't have to. You could leave it as 3 out of 36. Here's a similar question that I want to work with you. 2 dice are rolled. What's the probability that the sum of the faces is less than 5? So the key here to this one is we've been asked, what is the probability that the sum of the faces is less than 5? So probability that the sum is less than 5. You don't necessarily have to do it this way, but I'm kind of think about, okay, what is it that I'm looking for then? Sum's less than 5. So if I get a sum of 2 dice, I could have a 2, I could have a 3, I could have a 4, I could have a 5. Wait a minute, I need the sum to be less than 5, so I don't want the 5 to be in there. So I'm looking for successes where the sum of my dice is 2 or 3 or 4. There's more than one way to have a success here, so I need to find all those successes and add them together. All the 2s, all the 3s, and all the 4s, I'm going to add them together. So we'll go back and we'll take a look. See if I can do some erasing here. I'm not sure. I don't have a trash can anymore. I apologize. Let me see if I can do it this way. Not elegant, but it got the job done. Okay, now I need anything that's less than 5. So let's see, this is 5, so that's no good. That's 3 and 1, make a 4, 2 and 2, 3 and 1, 1 and 2, 2 and 1, 1 and 1. And then this is 5, this is 5, this is 5, this is 5, and everything down here is bigger than 5, so I don't want any of those. So what I've come up with here then, it looks like I have 1, 2, 3, 4, 5, 6 successes. I still have those same 36 outcomes. So the probability that I get a sum less than 5 is 6 out of 36. I could reduce that to 1/6 if I wanted to, or I could just leave it as 6 out of 36. That's totally fine. Let me know if you have any questions on any of that with the dice rolls. Outstanding. Sorry for my frustration in not being able to erase. The words and or are going to be important for us as we talk about probabilities. And so we're going to talk about the difference between those words. They don't appear to be that different, but they really, really are for us. The word and. If and is involved in a probability question, to be a success, both things must happen. We have to have the first thing and the second thing. Thinking way back into Math 122, this is similar to intersection. We need the first thing and the second thing. And went with intersection back then, and here, we need both things. So it is sort of reminiscent of intersection back from Math 122. The word or. There are 2 different uses of the word or, and I want to talk about those first. The word or. When you go to a restaurant and the waiter walks up and says, "Do you want soup or salad?" What that means is you can have one or the other, but not both. That's called exclusive or. One or the other, but you can't have both. Different from this, if you were to walk down the street and find a hot dog vendor and they ask you if you want ketchup or mustard, you could have ketchup, you could have mustard, but you could have both if you want. That's what's known as inclusive or, because both is okay. And inclusive or is the type of or that we use in mathematics. So we're talking about inclusive or. It could be the first thing or the second thing, or it could be both. That's fine too. And so the way we're going to describe or is, if we see or in a problem to be a success, at least one of the things must happen. The first thing could happen, or the second thing could happen. And if they both do, that's totally fine. At least one of the things must happen for us to have a success. Let's see where we might use this type of command in a problem, and that would be in problems involving a deck of cards. Some of you may be very familiar with a deck of cards and what it's made up of. Some of you might not, and because of that, I'm going to go ahead and sort of give you the overview of the anatomy of a deck of cards. If you're already familiar with the deck of cards, this may not hold a whole lot of value for you, but just in case somebody's not that familiar, I want to make sure we're all comfortable with the types of questions we might see. First and foremost, there are a total of 52 cards in the deck. So that's how many we have total. And you can see all 52 right there in this picture. At a quick glance, you can see that half of those 52 cards, 26 of them, are red. And half of them, 26 of them, are black. We have 4 things that are called suits. There are 4 suits, and those suits are the pictures that are on the cards. We have hearts, diamonds. Those are called clubs. As a little kid, we always called them puppy feet, but they're called clubs. And then these look like a shovel down here are called spades. So we have hearts, diamonds, clubs, and spades. Those are our 4 suits. And then within each suit, you can see the cards that make up every one of those suits. We have an ace, which is like a 1. and then 2, 3, 4, 5, 6, 7, 8, 9, 10. We don't have 11, 12, 13. Instead, what we have here is a jack, a queen, and a king. And that jack, queen, and king there at the end, because those have pictures on them, sometimes the jack, the queen, and the king are referred to as face cards because they have face cards on them. And so that's what makes up a deck of cards. One thing to make a quick note of is that there are 13 hearts, 13 diamonds, 13 clubs, and 13 spades. And that's how we get to the 52 cards total. Anybody have questions about the anatomy of a deck of cards before we start doing some questions that involve a deck of cards? Okay, very good. One card is drawn from a standard deck. Find the probability of getting a 7. Remember, that's what this notation means, is the probability of getting the thing that's in parentheses. And so the probability of getting a 7. Remember, most important thing about probability is successes over outcomes. Probability is successes over outcomes. And if anybody wants to type in the probability of getting a 7, that's totally fine with me. I'm not going to do a poll for this. So if some of you are right there ready to do it, feel free. Go right ahead. Excellent. Lots of 4 out of 52s. If you're not sure where those 4 out of 52s came from, that's okay. We're going to go take a look at it. But one thing we know right away, we almost get this for free, is the number of outcomes. Well, we're drawing a card from a deck, and a deck has 52 cards. So if I'm drawing one of those, then there are 52 possible outcomes. Now what we need to do is go find our successes. And our successes here would be the 7s. So we need to go back and take a look here and find our 7s. So let's see. I've got a 7 of hearts, a 7 of diamonds, a 7 of clubs, and a 7 of spades. That's it. That's all my successes in this deck. So I have 4 successes and 52 outcomes. So my probability of getting a 7 is 4 out of 52. You could reduce that to 2 out of 26. I don't know why you would, but you could. You could reduce that to 1 out of 13, but you don't have to. It's perfectly fine to leave it as 4 out of 52. Okay, the second question is a little bit strange. What's the probability of getting a card that is not a diamond? So anything but a diamond. There's 2 different ways you can approach this problem, and they're both fine with me. I think for most part, we're gonna, and again, you can type it in if you want to. For most people, you're just gonna do it just the way we've done everything else and find successes over outcomes. So I need to get a card that's not a diamond. Well, there's 52 cards in the deck, and then the successes would be any of those that's not a diamond. Yeah, Summer, you're good. So anything that's not a diamond would be a success. So that's all 13 of these, all 13 of these, and all 13 of these. So altogether then, I guess I've got 39 cards there that are not diamonds. So since I have 39 cards altogether that aren't diamonds, that means I have 39 successes out of my 52 outcomes. So the probability of getting a card that's not a diamond is 39 out of 52. You could reduce that down to 3/4 if you wanted to, but 39 out of 52 is just fine. If you put 3/4 as an answer here, it'd be correct. So, you know, that's perfectly fine. If you were to see it that way right out of the gate, if you're like, well, 1, 2, 3/4 of the cards here aren't diamonds, so my probability is 3/4. Okay. Well, since I mentioned it, I said there were 2 ways to do that problem. That's what most people would do, but I don't want to leave this out. What some people might do is say, well, what if I find the probability of getting a diamond and then use that to find the probability of not getting a diamond? Not many people would do it this way, but you might, so I at least want to see it. probability of getting a diamond would be 13 out of 52. And then like, okay, I don't want a diamond. So the probability of everything, all the cards in the deck, well, that's 52 out of 52. If I subtract the 13 diamonds, and this is kind of nice because we get to review subtracting fractions. So if I say, okay, here's everything that could happen. And right now what I'm going to do is I'm going to subtract the probability of getting a diamond. And that'll leave me with the probability of not getting a diamond. And so to do that, what we'll do is subtract those. Let's see. I have a common denominator, so I can subtract. Denominator stays the same. 52 minus 13 in the numerators is 39. Sure enough, I get 39 out of 52. Same thing I would have gotten the other way. Either approach is fine. My guess is that the vast majority of you did this. Okay. One card is drawn from a standard deck. We'll do these one at a time. Feel free to type it in whenever you're confident. And even if you're not that confident, it's okay. The first one is, what's the probability of getting a 7 and a heart? The word and, extremely important here. We're going to draw one card from the deck. What's the probability that the card I get is a 7 and a heart? And if you have something different than other people are typing in, you don't have to, recoil or feel like you have the wrong thing. You might have the right thing. This is one that, warrants discussion. That's not to say that what the people typed is necessarily wrong. I'm just, trying to spark you all being confident enough to throw it out there. Okay, let's see what we've got. So a 7 and a heart. I'm drawing one card from a standard deck. The denominator here comes easily. That's just 52. Now I have to find my successes. And I'm looking for cards that are a 7 and a heart. So let's see. When I go back and I want to find a card that is a 7 and a heart. Okay, well, that's a 7 and a heart. That's a 7, but it's not a heart, it's a diamond. And that's a 7, but it's not a heart, it's a club. And that's a 7, but it's not a heart, it's a spade. So you know what? Sure enough, there is only one card in this whole deck. There's a 7 and a heart, and it's right there, the 7 of hearts. That's the only one. So we have one success and 52 outcomes. So Jennifer Summer, you're exactly right. Our probability of getting a 7 and a heart is 1 out of 52. Okay, let's look at that question down there at the bottom now. What's the probability of getting a 7 or a heart? So now the word changed from and to or. That changes what my successes are going to be. All right, we've got a 17 out of 52, a 16 out of 52. I'm not sure what else might come our way. Another 16. Another 16. Okay, looks like those 16s are pretty powerful here. And Summer may have changed her mind, or she may want to stand up. Oh, okay, she's back with the 16. All right, well, to start out with, we know we're taking one card from the deck, so there's 52 outcomes. Let's go see what our successes are. Very good, Summer. That's perfect. So we go back and we see what our successes are. And here, I'm looking for a 7 or a heart. Okay, the word or means all the 7s count, all the hearts count, or if it happens to be both, it counts. So, well, I know there's 4 7s in the deck, and I know there's 13 hearts in the deck, so sure enough, 17 successes. Why is that no good? Those of you that said 16 out of 52, how come that doesn't work? Excellent. Jennifer, Shelby, you're exactly right. This is no good because if we do that, we're counting the 7 of hearts twice, one way or the other. If we go through and count all the hearts, right? So we'll count up all the hearts. So we've got those 13 successes. And now I'm going to count the 7s, and I have 1, 2, 3, 4. Wait a minute. I've counted this card twice. I don't want to do that. So it's not as simple as saying there are 4 of these. Oops. It's not as simple as saying there are 4 of these and 13 of these. We can't do that. We really need to think about what those successes are going to be. Make sure we don't count anything twice. And that's what we've got here. We have the 13 hearts and then the 3 other sevens to get to 16. Or if you wanted to, you could have the 4 sevens and then the 12 other hearts. Either way that makes sense in your head to end up with 16 successes. So the probability of getting a 7 or a heart is 16 out of 52. Here again, I don't know why you would, but you could reduce that to 8 out of 26. You could reduce it to 4 out of 13, but 16 out of 52 is just fine. One thing that's really important about this page that I want to take a second to mention is probability of 7 and a heart, probability of 7 or a heart. The only thing that's different about those is one word right there, but the answer is significantly different from the other one. So make sure you have an understanding of the words and or, and make sure that you pay attention to that when you go looking for your successes. And if you have any questions on the distinction between and or, you let me know. For and, both things have to happen. We have to have a 7 and it has to be a heart. For or, if it's a 7, it's good enough. If it's a heart, it's good enough. If it happens to be both, that's fine. We're going to count that too. The 7 of hearts, we're not going to kick it out. We're going to keep it. So the 7 of hearts gets to stick around also. Any questions about any of that? All right, fantastic. A multiple event activity where we're not just rolling a die or rolling a pair of die or drawing a card from a deck. In this one, we are going to flip a coin, and then when that's done, we're going to roll a die. So let's see. A coin is flipped, and then a 6-sided die is rolled. So we're going to do both of these things. We could do them at the same time. That's fine. You could roll a die with one hand and flip a coin with the other at the same time and see what the result would be. And then we're asked for a probability down there. My first question to you is, if I wanted to write down this sample space, how many different outcomes are there going to be in this sample space? And really what I'm asking you about is the fundamental principle of counting from last week. Outstanding, Jennifer. I don't think that's always easy to see. So it's really good. The idea here is we have our coin and then we have our die. And on the coin, there are 2 outcomes, heads or tails. On the die, there are 6 outcomes, 1 through 6. Fundamental principle of counting tells us, find the number of possibilities for each stage in the problem, the coin and then the die, and multiply those together. And so all together, we're going to have 12 outcomes. All right, let's see if we can list those then. Well, I could get heads with a 1, heads with a 2, heads with a 3, heads with a 4, heads with a 5, heads with a 6, tails with a 1, tails with a 2, tails with a 3, tails with a 4, tails with a 5, and tails with a 6. I knew I needed 12. Kind of nice to do this ahead of time to know once I list out 12 different things, I've got them all. So I've got them all. Now we go over here and we look at this question and it says, find the probability of getting heads and an odd number. I know I'm going to have 12 outcomes, so that's my denominator. Now I just need to figure out my successes. What's this probability going to be of getting heads and an odd number? And I like the question mark, Shelby. It lets me know that here's my answer, but I'm not 100% confident about it. That's great. That's beautiful information to share with me. Okay, Nadine's got 3 out of 12. And this one's about the word and also. The meaning of and hasn't changed. So we're still using and the same way that we did before. And that's important to be aware of. Oh, okay, Shelby. Very good. Very good. That's excellent. Whenever you can catch your own mistake, that's perfect. So one of the things here is, we have a sample space that has 12 in it. Um, when it only has 12 outcomes, I think it's worthwhile to go ahead and just jot them down. And then we can identify the successes really easily. And here, as I look at it, I need heads and an odd number. So heads and an odd number. Yes, that worked. This is heads, but it's even, so that's no good. Heads and odd number. Yep. Heads and even, no good. Heads and odd, so that's good. Heads and even is no good. And I have to have heads and an odd number. So anything that doesn't have heads is not going to work. So I wind up with 3 successes out of 12 outcomes. We could reduce this to 1/4, or we could just leave it as 3/12. One other thing that we can do with probabilities, and we will certainly see this as we go forward, is we can write them as fractions, but we can also write them as decimals. And so if you come up with a probability like 3/12, and you're asked, write your answer as a decimal, because you'll be asked for both. Write it as a fraction sometimes, write it as a decimal sometimes. If we want to write this as a decimal, all we need to do is divide. This is 3 divided by 12. And so we'll kind of go over and do 3 divided by 12. I get 0.25. And so as a fraction, my answer here would be 3/12, which I could reduce to 1/4 if I wanted to. As a decimal rounded to the nearest hundredth, it would just be 0.25. And so if you're ever asked for a probability in the form of a decimal, you'll go through the same steps we've been doing all day long, where successes over outcomes to get the fraction. And then one extra step is to divide numerator divided by denominator, and that'll give us the decimal version of that probability. Any questions on this before I have you try one like it? Awesome. Here goes. A coin is flipped and a 6-sided die is rolled. Find the probability of getting tails or an odd number. I'll make a poll for this and let you try. All right, we'll go another 20 seconds on this one, and then we'll talk through it together. All right, let's see. I really don't like that reporting. Can't even see what all the answers are. I'm going to see if I can change some settings around somewhere. But we are kind of spread around on this one. So let's be really patient and careful as we go through it. That's more important than anything else. So if we go through this and see anything that you're unsure of or doesn't make sense, make sure you ask about it. This is more complex, I think, than most of the problems we've worked on today. Just like before, we have a coin that we're going to flip and a die that we're going to roll. And so as we do that, what we're going to see is, well, there are 2 possibilities on the coin, 6 on the die, so there's 12 outcomes altogether. And so we can write those down, and we'll have heads with 1, 2, 3, 4, 5, 6. Tails with 1, 2, 3, 4, 5, 6. And this is a probability question. Most important thing about probability is that probability is always going to be successes over outcomes. No matter how complicated our probability questions might get over the next couple of weeks, it all boils down to successes over outcomes. No matter how simple or complicated a probability question is, that's where we're going. Okay, so, well, there are 12 different things that can happen here. So I have 12 outcomes. So our denominator is definitely going to be 12. And everybody responded with that. So that's good news. Now we have to identify our successes. And I think a key here is the word or. And the idea behind the word or is at least. At least one of those things has to be true for this to be a success. If there's a tails, it's a success. If there's an odd number, it's a success. If it happens to be both, great, that's a success too. All right, so tails or an odd number. Well, this outcome right here, heads with a 1, it doesn't have a tails, but it does have an odd number, so that's a success. Heads with a 2, doesn't have tails, doesn't have odd, that's no good. Heads and a 3, doesn't have tails, but it does have an odd number. Heads and a 4, doesn't have tails, doesn't have an odd number, so that's got neither. That's no good. We need at least 1 to be a success. Heads and a 5, doesn't have tails, but it does have an odd number. Heads and a 6, doesn't have tails, doesn't have an odd. That's no good. And then over here, well, if it has tails, we're going to call it a success. Well, every one of these has tails in it, so whether it has an odd or an even doesn't really matter. If it's got tails, it's good enough. So all those are successes. And now we count them up. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9 successes out of 12 outcomes. So we could rewrite that as 9/12. If we wanted to reduce it, we could call it 3/4. If we were asked to write it as a decimal, 9 divided by 12 would give us 0.75. One thing I do want to say here before we move on from this one is, if this question had said, find the probability of tails and an odd number, now you would have to have tails and an odd number. You would have to have both of these things to be a success. So if it had said that, tails and an odd number, now tails with a 1, tails with a 3, tails with a 5, those would be the only successes we have. Because and means you have to have both. And this doesn't have an odd number, and this doesn't have an odd number, and this doesn't have an odd number, and these don't have tails. And so that's the difference between and or, is whether or not we need both things to happen, or we just need at least one. Anybody have any questions?